Welcome to Textile Recycling Technologies, an open educational resource part of Block 6, Sustainability, developed by Materially, an international agency specialized in consulting and scouting solutions for innovation starting from materials. Textile fiber recycling may be performed via mechanical or chemical recycling, the latter being less commonly used since it still represents a scenario under development. Available solutions may require further perfecting or not be economically convenient or suitable yet for Excel volumes, as the market may require. Recycling processes via thermomechanical means frequently result in a loss of mechanical properties and overall performances. However, they still represent the most frequently adopted recycling solution, even though chemical recycling leads to higher quality outcomes. Mechanical recycling represents the basal process for recycling textile materials and consists in deconstructing the fabrics mechanically to obtain reusable fibers and material in an effective way. In the case of natural fibers, the resulting process outcomes are ready to be used to manufacture new yarns or new textile products. However, they exhibit reduced quality features due to the fact that the fibers are shortened and damaged during the shredding process and may require blending with additional fibers in order to create durable resulting fabrics. Chemical recycling processes transform waste textile materials by means of specific chemical processes and enable the production of new fibers featuring properties that are equivalent to those of the initial fibers, or maybe even better. Since these technologies are based on chemicals, they should rely on their reuse in order to be environmentally sustainable, also from the point of view of the process itself. More uniform and homogeneous materials featuring low to zero amounts of colorants, dyes, finishings, prints, and toxic substances have greater chances to be returned to X-cycle, but blends and chemicals do not represent the only obstacle to effective and efficient recycling procedures. In the case of finished garments, the construction and recycling procedures are complicated and decelerated by sewing threads featuring different compositions than the garment's material, as well as by buttons, zippers, closures, studs, and further rigid components. This OER offers an introduction to advanced textile recycling technologies, and in particular a case study selection to illustrate the state-of-the-art of these recycling technologies. Chemical textile recycling technologies. The OER aims are to provide students knowledge about advanced textile recycling technologies. In order to illustrate their state-of-the-art, and especially the state-of-the-art of chemical textile recycling technologies, a selection of case studies of commercially available products and processes has been evaluated. Our first case study is an advanced chemical recycling process which turns non-reusable products, such as blended polyester and cotton clothing and textiles, PET plastic bottles and packaging, into virgin equivalent raw materials ready to be put back into production and supply chains. Conventional recycling methods are unsuitable for polycotton blended textiles, which make up most textiles and require to be separated back into polyester and cotton. This advanced recycling technology is able to strip out dyes and finishes and separate, decontaminate, and extract polyester and cellulose from non-reusable textiles and polyester bottles and packaging to produce dual PET and cellulose outputs. The developing company was awarded a grant to become the first chemical recycling technology to be cradle-to-cradle certified. Our next case study is an enzyme-based recycling process based on the use of enzymes, which can be considered highly specific biological tools as defined by the manufacturing company. This innovative approach enables the specific depolymerization of a single polymer, for example PET, contained in the various plastics to be recycled. This process results in monomers that are purified in order to be repolymerized, thus enabling a perpetual recycling process. If plastic residues occur that are not degraded during the first stage, they are depolymerized in a second stage by means of the same process, but by applying a different enzyme that will depolymerize other polymers in the same way as in the first stage. Among plastic waste, this enzymatic technology is particularly suited for polyesters and polyamides. These polymers feature monomers chains that are easily identifiable by the enzymes and are therefore easier to depolymerize. In addition to textile waste, this technology is suitable for plastic bottles and containers, packaging and films. Biologically recycled PET exhibits the same property as petrochemical PET, but can be produced from enzymatically depolymerized PET waste. Polyester is classified as today's single largest volume fiber produced globally, taking about a 50% share of the overall fiber market. This technology enables to depolymerize 100% PET textile waste fibers into their original monomers, PTA and MEG. Our next case study is the patented recycling technology, which is able to transform high cellulosic waste into pure, natural dissolving pulp. This efficient chemical process does not use any solvents but sustainable chemicals that are recycled in the process and was developed in response to the issue of waste generated by the fashion industry and allows for the closed-loop recycling of cellulosic textiles by reusing discarded textiles to create reduced environmental impact new textile products. This recycling system uses less water and chemical and emits as well less CO2 than existing conventional processes used to manufacture clothing fibers. The company's plant is powered by 100% green energy from wind and water. Our next case study is the patent-pending closed-loop manufacturing system for apparel that repurposes mixed discarded post-consumer and post-industrial textile products. The resulting materials are upcycled yarns and fabrics composed of 70% post-consumer discarded clothing and 30% polyester. The material is naturally flame retardant and water resistant due to the upcycled polyester content and is commercially tested for furniture and building applications. The process recycles virtually all types of post-consumer garments and textile waste without having to sort or cut buttons, zippers, tags, etc. by using state-of-the-art technology that applies high-pressure air to separate fabrics from notions, preparing them for the subsequent mechanical process. It does not require any water, dyes, or harsh chemicals, which leads to additional savings on water usage and greenhouse gas emissions. Next is a processing system that converts pre- and post-consumer 100% synthetic and synthetic blend textile waste into recycled fiber, yarns, and fabrics. The technology is capable of managing complex blends, including stretch fabrics, which are typically different to handle with conventional techniques, and fabrics featuring recycled polyester. An overview of this specific recycling process. And next is a patented technology which can turn textile, cardboard, and agricultural waste into new natural fiber without any decrease in the quality of the fiber itself. Regardless of the raw material's origin, the process may be performed not just once or a limited number of times, but infinitely, while obtaining the same results in terms of output quality. The core of the technology consists of three key processes: activation, dissolving, and fractioning. The technology offers significant economical and ecological advantages and may fit into any existing pulp and viscose fiber plant. The resulting high-performance fiber has a natural hand feel, similar to cotton, 30 to 40% higher color uptake, and natural antibacterial properties. The new chemically regenerated fibers are suitable for the fashion and technical textile industries and can replace viscose and cotton in several applications. This technology requires considerably less water for production than cotton, and less forest needs to be harvested than viscose. The company's business model is to license this technology for global fiber producers in textile and non-woven industries. The end-use applications include fashion, home textiles, disposable personal care products, and technical products as well. The business model of the manufacturing company is to license this technology for global fiber producers in textiles and non-woven industries. The end-use applications include fashion, home textiles, disposable personal care products, and technical products as well. This short OER provided a series of case studies to illustrate how technological innovation contributes to the effectiveness of textile recycling. Please visit testexproject.eu to see more of the intellectual outputs of this project. Thank you for your attention.